9.2, conservation of momentum. This is the last section in Chapter 9, so you can you'll be having a Chapter 8, Chapter 9 test shortly. It will be after Thanksgiving break, so don't sweat it. Relax, enjoy break, but it'll be after break. So what we have to talk about is we're continuing to talk about momentum, and one of the key things about momentum was, remember, we said momentum is equal to mass times velocity. That is excellent. When we talk about momentum, we can talk about collisions and how collisions is conserved, or when a collision happens, momentum is conserved within a collision. We talk about conservation of anything, whether it's energy or mass or anything we've talked about in science so far. The principle is the same in the fact that in a closed, isolated system, whatever is being conserved doesn't change. It can only be gained or lost. So when we talk about the law of conservation of momentum, it is stating that momentum in a closed, isolated system can never be lost. It has to be changed. So it can be gained or lost by another object. And when we talk about the conservation of momentum, we're talking about two objects. When they collide, they still conserve momentum. So we're talking about the initial momentum of A, which would be ma times the initial velocity of A, plus momentum of B, which would be mb times the initial velocity of B, which is equal to the final momentum of A, which is mass of A times the final velocity of A, plus the momentum of B, which is mass of B times the final velocity of B. Now, it's very possible that occasionally masses will collide and stick together, and if that is the case, you're really just going to have one equation. You're going to take ma, mass of A plus B, times the final velocity. So if they stick together, that is what you'll have to have there. So we're talking about this is in really one dimension. I have a car driving south. I have a car driving north. They collide. That's a one-directional collision. We will get to two-directional collisions. So what we're really doing is we're taking the law of conservation of momentum and the equation at the bottom of the screen, which is the conservation of momentum equation, and we're going to apply it in three different ways. So the first example in which we are going to do that in is a very simple way to do it, and what we just talked about. We have two cars traveling in the same direction. So an 1,875 kilogram car is going 23 meters per second. It rear ends a 1,025 kilogram compact car going 17 meters per second on ice in the same direction. Must be black ice. The two cars stick together. How fast do the cars move together after the collision? So this is a classic conservation of momentum equation. So we're going to initial momentum of A plus initial momentum of B is equal to the final velocity, the final momentum of A plus the final momentum of B. Now, one kicker with this is that the two cars have collided together, so we're going to add the masses of the two cars together. So really it's going to be ma VAI plus MB VBI is equal to M A plus B times VF. Well, when you sit down and you go ahead and you plug everything in, we're just going to make the first car A and the compact car B. So A, the mass of the car is 1875 times the initial velocity, 23, plus MB, which is 1025, times its initial velocity, which is 17, is equal to the mass of the cars together, so 1875 plus 1025 times VF, and we are looking for VF. Well, when you break everything down and you go ahead and you do the math, you end up getting 43,125 plus 17,425 is equal to 2,900 times VF. You add the 43,000 together, you get 60,550 is equal to 2,900 times VF. Divide by 2,900. And your final equation for VF, or your final answer for VF in 2 sig figs, because we're limited by 2 sig figs, ends up being 21 meters per second. So that is the first way in which you can use the conservation momentum equation. The second way is recoil, where essentially you have no initial momentum whatsoever. Your initial momentum is at rest, but you're going to have one object go in one direction and the other object go in the opposite direction. So for example, most of you have probably fired a gun before. All right. When you fire a gun, what happens? The bullet goes forward. Boom, the gun recoils back into your shoulder, and that's momentum. The momentum of that bullet is equal to the momentum of the recoil of the gun going back into your shoulder. We could also look at it for a rocket. All right? The amount of momentum for the rocket going forward is equal to the amount of momentum of the gas expelling out the back. So a rocket starts at rest, then it starts to go. A gun essentially starts at rest, but then you have something going one direction and something going the exact opposite direction. And that is what recoil is, a pushing result. So if we take the conservation of momentum equation and we apply it to recoil, so we're going to have the very same exact thing that we had before. Same equation, just a little different application. So when we go ahead and do that, an astronaut at rest in space fires a thruster pistol that expels 35 grams of hot gas at 875 meters per second. The combined mass of the astronaut and the pistol is 84 kilograms. How fast and in what direction is the astronaut moving after firing the pistol? Well, again, this is going to be a conservation of momentum question. So we know initial momentum of A plus initial momentum of B is equal to final momentum of A plus final momentum of B. Same thing, we know that momentum is equal to ma times the initial velocity of A plus mb times the initial velocity of B, which is equal to ma times the final velocity of A plus mb times the final velocity of B. Well, let's go ahead and plug this in. Here's the doozy, though. For the first one, we know the mass of the astronaut is, we'll say the astronaut is A and the gun is B. So the astronaut is A and the thruster pistol is B. Well, the mass of the astronaut is 84, but he is starting at rest, so his initial velocity is 0, right, plus the thruster pistol, 35 grams. It's in 35 grams. Remember, when we're dealing with mass, everything has to be in kilograms, so it's going to be 0.035. But again, the initial velocity of the thruster pistol is 0, is equal to the mass of the astronaut, 84, times the velocity of the astronaut, and that's what we're looking for. So we don't know that. Plus the mass of the gas that is expelled, 0.035, times 875. We go ahead and we do the math. We're stuck with 0 is equal to 84 VF plus 30.625. Now to solve algebraically, you're going to subtract 1 over to the other side. When I go ahead and do that, I'm just going to subtract my negative 30 over. We get negative 30.625 is equal to 84 times VF. We divide by 84. We divide by 84. And VF ends up being negative 0.36. meters per second. We are confined to 2 sig figs because we had 2 sig figs with the 35 grams of the thruster gas. Also, the question asks, in what direction is the astronaut moving? The astronaut's going to be moving at negative 0.36, so it's going to be moving in the opposite direction of the direction in which he fired the bullet, the exact opposite direction. So that is recoil. You have initial velocities are 0, but you are essentially going in the opposite direction of your expulsion force. So a rocket and a gas, or a bullet and a recoil, that's kind of how recoil works. So we've used conservation of momentum equation in 2 ways. The third way that we can use this is that we can talk about collisions in 2D, which means we're going to have a collision on the X and a collision on the Y and a collision on the X. And where is that going to go? You can essentially imagine this as a recreation of 2 cars are getting T-boned at an intersection. Why did the cars end up in the ditch in a particular manner? So you're still dealing with the conservation of momentum, but you're dealing with multiple directions. So we're going to have to start dealing with some of our triangle stuff. So here's our third and final example. All right. A 1,325 kilogram car is moving north at 27 meters per second and collides with a 2,165 kilogram truck moving east at 11 meters per second. In what direction and what speed do they move after the collision? Well, you're still going to have to solve for momentum. Now, we have a 2-directional collision. So we have a car traveling east T-boning a car traveling north. What we are going to want to solve for is this value. We're going to want to solve for the hypotenuse, and we're going to want to solve for this angle. So the very first thing that we are going to want to do is we are going to want to figure out the initial momentums of both vehicles. So the first vehicle is moving north. So I will do that in green since my north arrow was in green. The initial velocity is equal to ma times va. That is equal to 1325 times 27.0. And when you do that with sig figs, and don't worry about sig figs because this isn't our final answer yet. When you take 1325 times 27, you get 35,775. So I'm going to take this value and we're going to go over here, 35,775. Next up, I'm going to solve for my initial velocity in the eastbound direction, or in the x direction. Same equation, except it's going to be mb times vbi. And when I do that, my mass of the truck was 2165 kilograms. It was traveling at 11 meters per second. 2165 times 11 is 23,815. So now I have 23,815. Well, I have my initial momentum A, or in the northbound direction. I have my initial momentum B in the eastbound direction. What I can do is when they collide, I can find my final momentum. I'm going to find my final momentum simply by doing the Pythagorean theorem. So PF squared is equal to PA squared plus PB squared. And that is equal to 23,815 squared plus 35,775 squared. You take the square roots of those, and you end up finding that the final momentum ends up being 42,976. So we have the final momentum. What we don't have is what it's asking, in what direction and with what speed. So we are going to have to find the speed at which that is moving. Well, we should be able to do that because we have the final momentum. So final momentum is going to be equal to ma plus b times vf. You can assume they stick together in this collision. The two cars stick together. So our final momentum that we figured out in the triangle is 42,976. That is equal to 2165 times, plus 1325. We're taking the masses of both vehicles and adding them together times VF. When we add these together, we end up with 3490 times VF. We're going to divide by 3490. We're going to divide by 3490, and we're going to get that VF is equal to 12.3 meters per second. So the last thing that we need to do is we figured out that our cars are going to go into the ditch when they collide at 12.3 meters per second. But the question asks, in what direction? So we are going to need to solve for this angle. Well, tangent is equal to opposite over adjacent. So if I take theta is equal to the tangent -1 of my opposite over adjacent, which is equal to my tangent -1 of 35,775 divided by 23,815. When I do that, I end up figuring that my angle is 56.3 degrees. Now, what you also have to classify is we had north and east classified. This was east and this was north. This is my angle, which is most definitely north of east. So that is my final equation. 12.3 meters per second at 56.3 degrees north of east. So we have conservation of momentum. We're going to use the equation in 3 different ways, just solving for momentum, in recoil, and in 2-directional collisions with triangles. It's a good way to sum up the chapter. We'll have plenty of review questions on this. If you have questions, you can talk to me tomorrow in class.